Hello, I'm Mike McCulloch. So today I thought I would tackle the subject of time, which is a complicated one, but an interesting one, because I think it's one of the major problems facing physics today. I think time in physics is handled very badly. So to start off with, I suppose I should go back to the paper by Einstein-Podolsky and Rosen in 1935. So what they proposed was the following thought experiment: that you have two particles which start off in one part of the universe together, and then they separate for some reason, and then when you wait for a long time, so they're very far apart, you measure one of them, the spin of one of them, which is a physical, well, a pseudo-physical characteristic, I suppose. You measure the spin of one of them and say it's up. So then you know, and the universe presumably knows, that the other one is spin down if they started with zero spin at the beginning. So the interesting thing about this, and it's called the Einstein-Podolsky-Rosen paradox, is that there is nothing in the wave function to encode the spin, so the particles can't carry the spin with them. Before they are measured, they are both a spin up and a spin down superposition. So as soon as you measure them, the issue is resolved. One of them becomes spin up and one of them becomes spin down. But how does the information about that get from the first particle that's measured to the other one, so it can decide whether it's spin up or spin down? So this implies that either something is wrong with quantum mechanics, in that we have to encode the spin in some sort of hidden variable, and this is what Einstein was arguing for, or there's something wrong with relativity and signals can travel faster than light, and you can have non-local effects. So I became very interested in this problem after reading The Emperor's New Mind by Roger Penrose back in 1991 at the end of my physics degree, just when I was starting my PhD, and I started playing around with Heisenberg's uncertainty principles, and this is kind of a very early precursor of quantized inertia. 1991, I was playing around with the energy time uncertainty principle, which is shown here. So we have dE, the uncertainty of the energy times the uncertainty in time has to be greater than h bar over 2. So in this formula we can replace the energy here with kT, so Boltzmann's constant times the temperature. But what is the temperature? Well, I wondered, what if it's the Unruh temperature? So that is, although back in 1991 I didn't know about the Unruh temperature, I had a different method. But more recently I wondered, what if it's the Unruh temperature? So temperature is h bar a over 2 pi ck. So if you put that in to this formula, you get this formula that says that the uncertainty in time is equal to pi c over a, where a is the acceleration of the system. So what does this mean? Well, it means that if the acceleration is extremely low in a system or a particle, then the uncertainty in time is very large, and this means that each now of time would dilate. So at the moment we are aware of a particular instant of time that this is now. Well, for a very low acceleration particle, that would extend. So for that particle, it would be able to access what to us would be the past or the future, but we would not, because we as biological organisms, we have a very high acceleration, so for us the now is very short. So this might explain the Einstein-Podolsky-Rosen problem or paradox, because these particles are do not as they're spreading out through the cosmos, they do not interact with anything else, so their acceleration is very low. And so for the Einstein-Podolsky-Rosen particles, their acceleration is incredibly low because they're not interacting with anything. And so that means that they can see what to us would seem to be the future and the past, and so they know what measurements are going to be made by us in the future already. So it's not a problem anymore. So I tried to submit this to journals much more recently. I tried to get it published, but as you might imagine, there was a lot of pushback from the journals. So I enlisted the help of Jaume Gine, who's from Spain, Catalonia, University of Catalonia, and he put the paper on a far more quantum mechanical technical formulation, and also pushed me an awful lot to get this finished and published. Even so, it took about 4 years, but we finally got it published in 2021, and it's the paper shown here. So the fundamental issue here is that it implies that time is not a dimension like space. It's an emergent property that depends on an object's interaction with its surroundings. If there's no interaction, there's no time, and I alluded to this in my book as well. So time becomes associated more with something like the concept of change. So time is change. Okay, so I hope you've enjoyed this short, and I look forward to talking to you again next time. Goodbye.